At the dawn of the 1960s, the United States Navy, the undisputed ruler of the world's oceans, found itself suddenly on the brink of obsolescence. Its mighty carrier battle groups, the very pinnacle of surface warfare, the platforms that had won the Pacific and secured the post-war order, were rendered vulnerable. They were being stalked by a new and unseen predator, a ghost in the deep ocean. The U.S. Navy was losing its eyes beneath the waves, its sensors deafened by a new kind of ocean war. A strategic paradigm shift had occurred, and the U.S. Navy was, for the first time, failing to see the single greatest threat to its existence. The source of this strategic nightmare was not a fleet of battleships or a squadron of bombers. It was the burgeoning, silent, and technologically revolutionary underwater fleet of the Soviet Union. This was a new kind of war, a three-dimensional war of acoustics, physics, and engineering, and the U.S. Navy was losing. Its multi-billion-dollar destroyers were functionally deaf, their sonar systems neutered by the ocean's own physics. Its carriers were being hunted by carrier killers, Soviet submarines that were, for the first time in history, faster than the ships trying to find them. The solution to this existential crisis would not come from a sleek new destroyer or revolutionary jet. It would come from an ugly duckling, a commercially failed propeller-driven civilian airliner. This aircraft, the Lockheed P-3 Orion, would be mocked by jet pilots and underestimated by adversaries. But in the hands of naval engineers, this failed plane was transformed into the most lethal and effective submarine hunter the world had ever seen. This is the story of the Orion Doctrine. It is the story of how a propeller plane stuffed with revolutionary sensors and one of the first truly integrated digital computers made the opaque, hostile ocean transparent. It is the story of the engineering and tactics that systematically broke the Soviet submarine fleet, terrorized its captains, and secured American dominance of the seas for more than half a century. To comprehend the Orion's revolutionary impact, one must first understand the profound systemic vulnerability it was designed to solve. The U.S. Navy of the late 1950s was not just losing the underwater war, it was failing to even comprehend its new rules. The Soviet Navy, building over 400 submarines in just 12 years after the war, most diesel, many newly nuclear, had engineered a three-pronged threat that targeted every pillar of American strategic power. First was the impossible problem of the nuclear-powered attack submarine, SSN. The introduction of the Soviet Project 627, or November-class, in 1959 was a technological earthquake. It fundamentally flipped the entire equation of anti-submarine warfare, ASW. For all of naval history, the hunter, the surface destroyer, had been faster than the prey. The November class, powered by a nuclear reactor, could sustain speeds approaching 30 knots underwater, faster than most destroyers could hunt. This single development rendered decades of Allied ASW experience and equipment worthless. The hunter was now slower than the hunted. The submarine, not the destroyer, dictated the terms of engagement. The November class could engage and disengage virtually at will, acting less like a prop-driven World War II U-boat and more like a jet fighter engaging a prop fighter. The ocean depths had become a realm where the predator was now the prey. Second was the tactical carrier killer. While the West feared the Wolfpack threat to its Atlantic supply lines, Soviet doctrine was focused on a more direct target, the U.S. Navy's carrier battle groups. New Soviet nuclear-powered guided missile submarines like the Echo and Charlie classes were not designed for strategic bombardment. They were dedicated carrier killers. Their sole mission was to find, stalk, and in the event of war, get close enough to launch swarms of large, powerful cruise missiles to destroy America's floating air bases before they could even launch their planes. Third was the strategic nuclear threat to the homeland. While the Echo-class hunted the fleet, the Hotel and later the formidable Yankee-class ballistic missile submarines, SSBN, were armed with nuclear weapons. These were the Soviet Union's ace in the hole, a survivable second strike force.
They would patrol in designated bastions in the Mid-Atlantic, holding cities from Washington, D.C. to New York hostage and threatening to launch a surprise first strike that could destroy U.S. bomber bases and Minutemen ICBMs before they could be launched. This three-part threat, the fast attack sub, the carrier killer, and the strategic boomer, created an existential trilemma. The Navy's entire doctrine was at risk, and the core of that failure was not in their weapons, but in their sensors. The Navy's doctrine was centered on its surface destroyer screens. By 1960, this doctrine was on the verge of catastrophic failure. The admission from naval officers at the time was stark. After 6 years of operating against our own nuclear submarines in war games, we still do not have at sea a weapon system able to cope with even one of them. The problem was twofold. First, as the November class had proven, many World War II-era destroyers were simply too slow. But the second, more critical failure was one of physics. Even new purpose-built frigates and destroyers were deaf. Their primary sensors were massive hull-mounted active sonar systems like the SQS-26. These systems, which required enormous power to send out an acoustic ping, were failing. The problem was the ocean itself. The ocean is not a uniform body of water. It is stratified into layers of different temperatures. The boundary between the warm surface water and the deep cold water is known as the thermal layer, or thermocline. This layer, a fundamental reality of oceanography, was a perfect shield for a submarine. Sound waves, especially the ping from an active sonar, bend or refract when they pass through water of different temperatures, always bending toward the colder, denser water. Sound bent and twisted by layers of cold and warmth, a perfect invisibility cloak. A Soviet submarine captain running quiet could take advantage of how sound waves act by hiding in the cold layer just below the thermocline. A destroyer's hull-mounted sonar system operating in the warm surface layer would emit a ping that upon hitting the cold thermal layer would bend dramatically. It often reflected off the layer itself as if it were a false ceiling, leaving the submarine below completely invisible. The surface Navy was functionally blind. Their Band-Aid solutions were a tacit admission of this failure. Systems like the Anti-Submarine rocket, ASROC, a ballistic rocket that hurled a torpedo miles away, were developed because their ships could no longer get close to a target. The Hunter was functionally blind, deaf, and slow, and its primary mission, protecting the carrier, was in existential jeopardy. If hunting from the sea was impossible, the solution was to hunt from the air. This single tactical pivot, born of desperation, solved the two most significant problems of surface ASW at a single stroke. First, mobility. A 30-knot nuclear submarine cannot outrun a 377-mile-per-hour aircraft. The entire engage and disengage at will advantage of the Soviet SSN was nullified. Second, physics. An aircraft is not bound by the thermal layer. It can fly over the ocean and drop its own sensors, sonobuoys, directly into the water column, deploying them below the layer where the submarine is hiding. In 1957, the Navy issued its formal specifications for this new Apex Hunter. The platform would have to meet a seemingly contradictory list of grueling engineering requirements. Extreme endurance, the ability to prowl the vast expanses of the ocean far from land for 12 hours or more. Low and slow loiter, the efficiency to fly at low altitudes, 1,500 feet or less, and at slow speeds for hours on end, monitoring sensors without burning excessive fuel. High-speed transit, the raw speed to get to a contact area hundreds of miles away quickly. Massive payload, the capacity to carry a flying sensor network of radar, electronics, and dozens of sonobuoys, and a full internal weapons bay of torpedoes and depth charges. Crew habitation. Finally, the Navy recognized that the mission's true limiting factor was not fuel, but crew fatigue. A 10-person crew on a 12-hour mission required a comfortable, pressurized, and spacious environment. They needed stand-up and walk-around space, a galley, and comfortable, adjustable chairs. The Navy needed a fast, long-range, high-endurance, heavy-lift aircraft that could also fly with the slow, sipping efficiency of a World War II prop plane. The solution would not be a sleek new jet. It would be a failed civilian airliner, an ugly duckling whose commercial disaster was about to become the Navy's greatest engineering triumph.
The aircraft that would become the Soviet Navy's worst nightmare was not a purpose-built military marvel. It was the Lockheed L-188 Electra, an advanced civilian turboprop airliner that, through a brilliant combination of circumstance, tragedy, and engineering, proved to be the perfect pre-hardened platform for the ASW mission. The L-188 Electra was born in the mid-1950s to meet airline requests for a fast, fuel-efficient turboprop airliner that could service the shorter runways common in the U.S., where pure jets were not yet practical. It was, for a brief time, a technical marvel. Its commercial career, however, was disastrous. Between 1959 and 1960, 4 fatal crashes, traced to a deadly vibration mode, saw aircraft seemingly disintegrate in midair. The flying public was terrified, and the Electra became a commercial pariah. A massive, high-priority investigation by Lockheed, the FAA, and NASA uncovered a new, terrifying, and previously unknown aerodynamic phenomenon, propeller whirl mode. The investigation found that a hard landing, a common survivable event in daily airline operations, could cause hidden, undiscovered damage to an engine mount. This weakened mount, lacking its designed structural stiffness, allowed the powerful gyroscopic forces of the large propeller to create an unstable wobbling motion. This oscillation, or whirl mode, would, under the right aerodynamic conditions, couple with the natural harmonic frequency of the wing itself. The resulting catastrophic flutter was powerful enough to fail the right wing, tearing it clean off the fuselage in seconds. In response, Lockheed initiated a massive, costly redesign and modification effort called the Lockheed Electra Achievement Program, or LEAP. This program fixed the flaw by dramatically strengthening the engine mounts, nacelles, and surrounding wing structures. The flaw was fixed, but the plane's commercial reputation was not. The Electra was a failed plane. For the U.S. Navy, the Electra's commercial failure was a spectacular stroke of luck. The Navy's selection of the airframe had actually been made in 1958, before the crashes. Now, the LEAP modification program meant the off-the-shelf airframe they were receiving was arguably the most structurally reinforced fuselage in history, perfectly suited for the brutal, punishing low-altitude patrols of maritime ASW. The Electra's core design met every one of the Navy's impossible requirements. Its 4 Allison T-56 turboprop engines, the same legendary engines used on the C-130 Hercules, were the key. Turboprops offered a perfect compromise that pure jets of the era could not. 1. They were incredibly fuel-efficient at the low altitudes and slow speeds required for on-station hunting. 2. They were immensely powerful, giving the aircraft the high-speed transit capability to get to a contact area quickly. This efficiency gave the P-3 Orion, as the military version was designated, a staggering unrefueled endurance of up to 17 hours, more than half a day in the air. This endurance was further enhanced by a unique tactical capability. For low-altitude, sea-level ASW work, P-3 crews could, and routinely did, shut down 2 of their 4 engines in mid-flight. This tactic, impossible on a twin-engine jet, dramatically reduced fuel burn and achieved increased time on station, allowing a P-3 to loiter over a target area for an entire shift.
The Electra's other failed commercial feature was its spacious, wide fuselage. Airlines had found it inefficient for seating, but for the Navy, it was a godsend. Compared to its cramped predecessor, the P-2V Neptune, the P-3 boasted 250% more floor area. This provided the stand-up and walk-around space and comfortable adjustable chairs that directly combated crew fatigue, the real mission killer on a 12-hour hunt. Most importantly, this big-body design gave the P-3 its 60-year service life. The massive fuselage was a blank slate, a truck that could be stuffed with electronics. This modularity meant the airframe could adapt as the mission evolved, from the analog systems of the 1960s to the digital revolution of the 1980s and beyond.
The Lockheed L-188 Electra airframe, hardened by its commercial failure, provided the U.S. Navy with the perfect truck. It was a robust, spacious, high-endurance platform that could operate for punishingly long hours at low altitude. But a truck is useless without its cargo. The true revolution, the engineering that transformed this ugly duckling into an apex predator, was the sophisticated, integrated system of sensors and computers packed deep within its fuselage. The P-3 was not just a plane, it was a flying sensor network, a system of systems designed to methodically find, fix, and finish a target in the opaque, three-dimensional battlespace of the deep ocean. The P-3's primary weapon was its ears, a massive payload of sonobuoys. The P-3C variant could carry up to 84 of these underwater microphones, 48 preloaded in pressurized launch tubes in the belly, and 36 more stored in racks inside the cabin for the crew to load by hand. This payload allowed the crew to seed a massive area of the ocean, creating a disposable wide-area sensor net. A common misconception born from Hollywood films is that the hunt begins with an active, aggressive ping. The reality is the exact opposite. The hunt is a quiet, patient, and methodical process, done almost entirely in passive mode so as not to alert the sub. Giving away the P-3's presence is the last thing a crew wants to do. The process is a careful, engineering-driven sequence. First, the crew must understand the battlefield. The first buoy dropped on station is always a bathythermograph buoy. This is a simple, non-acoustic sensor. It is a thermometer on a wire that drops to a depth of 1,800 feet, profiling the water's temperature at every level. This data is transmitted back to the P-3, instantly telling the crew where the thermal layers are. This data is critical. It allows the tactical coordinator, or TACO, to set the depth of the other sonobuoys, ordering them to listen below that layer, in the cold, deep channel where the submarine is most likely hiding. Second, the passive search. The crew then drops a field of passive buoys. These include LOFAR, which are simple, omnidirectional microphones that just listen. But the most important buoys are DIFAR. A DIFAR buoy is a LOFAR buoy with a crucial addition, a built-in magnetic compass. The DIFAR buoy's hydrophones detect the sound like the 60 Hz hum of a Soviet reactor pump. The internal compass simultaneously detects the bearing of that sound relative to magnetic north. This allows the buoy to transmit not just, "I hear something," but "I hear something in that specific direction." This is the key. A single DIFAR buoy gives the TACO a line of bearing, an ambiguous line pointing towards the target. By dropping a second and then a third DIFAR buoy, the ANU computer can instantly triangulate these bearings to create a fix, a small, calculated box on the tactical plot representing the submarine's probable location. Third, the active ping. Only when a submarine is localized, or, as the doctrine states, just before an attack run, does the crew go active. The pinger buoys, like the CAS,
command-activated sonobuoys system, are smart buoys. A P-3 can drop a barrier of cast buoys, leave them dormant and silent, and then, at the precise moment, transmit a coded signal to command them to activate. This gives the TACO total control of the acoustic battlefield, allowing him to box in a submarine and get a final perfect range and bearing for a weapons solution. The sonobuoy field, even with triangulation, provides a fix, but this ballpark can still be hundreds of yards across. For a torpedo, that is not precise enough for a kill. The P-3 needed a tool for the final, critical moment of targeting. This tool was its nose, the iconic Magnetic Anomaly Detector, MAD, housed in the long, distinctive stinger protruding from its tail. This sensor is a military-grade magnetometer, an instrument sensitive enough to detect tiny variations in the Earth's natural magnetic field. A 6,000-ton submarine is fundamentally a mass of ferromagnetic material. As this massive metal object moves through the ocean, it creates an invisible disturbance or magnetic anomaly in the Earth's field. The MAD sensor is just sensitive enough to detect this change as the plane flies directly over it. This sensitivity, however, is its greatest limitation. The strength of a magnetic field decays at the inverse cube of distance. This means that doubling the distance from the target doesn't reduce the signal by half. It reduces it by a factor of 8. Tripling the distance reduces it by a factor of 27. The signal vanishes almost instantly with altitude.
As a result, the MAD is not a long-range search tool. Its role is one of pinpointing, capable of detecting a metal hull from less than a kilometer away. It is primarily used for pinpointing the location of a submarine immediately prior to a torpedo or depth bomb attack. The sonobuoys get the P-3 in the right ballpark. The MAD provides the pinprick, the sudden hit on the operator's screen that tells the TACO the target is directly below us. Drop now. The Stinger's long, isolated design is a functional necessity, a perfect example of form following function. The sensor is so sensitive that it must be placed far from other electronics and ferrous metals on the aircraft to prevent the electromagnetic noise of the P-3's own engines, airframe, and electronics from interfering with the tiny, fleeting signal from the submarine below. This same design principle also revealed a potential counter-strategy. Soviet engineers, in a costly effort to defeat MAD, would later build entire submarine hulls out of non-ferrous titanium, like the Project 705 Alpha class, specifically to be invisible to this sensor. A nuclear submarine is blind. To navigate with certainty, to identify a target, or simply to get a message, it must periodically expose a mast, a periscope, a snorkel, or a communications antenna. This is its moment of extreme vulnerability, a brief 30-second window where it breaks the surface and can be seen. The P-3's eyes were engineered to exploit this moment. The AN/APS-115 radar, with antennas in the nose and tail providing 360-degree coverage, was designed to scan the vast ocean surface for small cross-sectional targets. The engineering challenge is immense. Detecting a small metal tube, a periscope, in the chaotic sea clutter of ocean waves is manually intensive. But this radar provided another critical layer in the P-3 sensor net. A Soviet captain could no longer be sure that a 30-second periscope exposure would go unnoticed. This was the apex engineering of the P-3 Orion, the single system that made it a legend. On their own, each sensor was powerful but imperfect. The passive DIFAR buoys gave ambiguous bearings. The MAD had a tiny range. The radar was confused by waves. On the early P-3A and P-3B models, these systems all had separate analog readouts. The tactical coordinator, or TACO, was overwhelmed with raw data, which he had to manually correlate, scribbling bearings on a plotting board with a grease pencil, performing trigonometry in his head, all while being bounced around at low altitude. It was slow, fatiguing, and hopelessly prone to error. The P-3C variant, introduced in 1969, changed everything. It was the result of the Navy's top-secret A-New project, and its centerpiece was one of the first aircraft to use a central digital computer for tactical operations. This computer, initially a UNIVAC CP901, was the brain of the aircraft. This computer was a revolutionary sensor fusion engine. It was engineered to integrate all information necessary to detect, localize, and kill an enemy sub. For the first time, the A-New system took the line of bearing from DIFAR buoy number 1, took the line of bearing from DIFAR buoy number 2, took the aircraft's own precise navigation data from its inertial systems, and it automatically performed the triangulation to create a fix, a precise updating target location on a screen. The system would then correlate this subsurface acoustic fix with a surface blip from the APS-115 radar. It displayed all this fused real-time data onto a single unified tactical plot for the entire crew. The TACO no longer had to guess, he could see. The A-New computer, in effect, made the ocean transparent. The P-3C, with its A-New computer, increased the possibilities of DIFAR threefold. The aircraft could calculate and cue its attack automatically, human reflexes guided by machine logic. It could even calculate the precise release point and feed that information directly to the pilots. The P-3C was no longer just a plane. It was a flying, digital apex predator. And with this new integrated weapon, the crews in the Atlantic began the hunt. With this revolutionary integrated technology, the P-3 Orion crews in the North Atlantic turned the tables on the Soviet submarine fleet. The hunter had definitively become the hunted. This transition from a blind defense to an aggressive offensive hunt was most evident over the strategic choke point that became the Cold War's single most important naval battlefield, the GIUK Gap. The GIUK Gap is the vast stretch of ocean between Greenland, Iceland, and the United Kingdom. This maritime choke point was the key to the defense of Europe. Any Soviet submarine from the powerful Northern Fleet based in Murmansk had to pass through this gap to break out into the North Atlantic, where it could threaten Allied shipping or the U.S. East Coast. This gap became the P-3 Orion's primary hunting ground. Flying relentless 12-hour patrols from bases like Keflavik, Iceland, P-3 crews prowled this cold gray stretch of sea, waiting for a clue. That clue would often come from SOSUS, the Sound Surveillance System, a top-secret global network of fixed hydrophones laid directly on the seabed. SOSUS would detect the faint sound print of a Soviet sub transiting from the port, and a P-3 would be scrambled to find it, fix its position, and track it. The stories from these patrols illustrate the P-3's total dominance. The first comeuppance for Soviet captains was the shocking realization that their stealth, their only defense, was gone. In one classic cat-and-mouse anecdote, as recalled by crews like retired Captain Tim Verhoff, a TACO on a P-3 from Squadron VP-6, his crew was scrambled from Guam in 1979 to find a Soviet Echo II-class carrier-killer SSGN. This sub was the Hunter, and it was confidently shadowing the USS Kitty Hawk carrier. Verhoff's crew found the sub and began stalking it passively as so not to alert the captain. Using only DIFAR buoys and their A-New computer, they developed good course, speed, and depth on the Soviet sub. The Echo II captain, completely unaware he was being watched from above, popped up at dawn to take a periscope look at his prey, the USS Kitty Hawk. What he saw instead, filling his periscope, was Verhoff's P-3 coming right at him on a low-level simulated attack run.
The shock was total. According to those who flew them, the Soviet skipper pulled the plug and went squirrely, doing that crazy Ivan thing where they dive and do a turn at the same time. The P-3 crew, all pretense of stealth now gone, switched to psychological warfare. They went active, dropping pingers, and as Verhoff put it, pinged the crap out of him while conducting more simulated attacks, forcing the carrier killer to detach from the Kitty Hawk and flee. The true comeuppance was not the occasional aggressive flyby. It was the psychological erosion, these cat-and-mouse hunting techniques that broke a submarine captain's will. The submarine's only strength, their only defense, is its stealth. The P-3 Orion, with its ANU computer and vast field of sonobuoys, systematically removed that stealth. This led to the terrifying tactic of holding down. Imagine you are a Soviet Akula-class submarine captain, commanding one of the quietest, most advanced boats in the Soviet fleet. You are deep, silent, and convinced you are invisible. Suddenly, your sonar operator hears a faint splash overhead, a sonobuoy. You have no idea where the P-3 is. You cannot see it, hear it, or shoot at it. You order a course change and a change of depth. Minutes later, splash, another sonobuoy. He turns hard to port. Splash, another. For the next 8 hours, the sub is held down. Every time it moves, another sonobuoy drops, the ANU computer instantly updating its tactical plot. The crew knows a plane they cannot see is perfectly, effortlessly tracking them, just waiting for them to make a mistake. They are no longer a predator. They are prey in a cage. The psychological stress on a crew in this confined space was immense. They were not just being hunted, they were being controlled. This total dominance was eventually confirmed at the highest levels. A quote often attributed to Soviet Marshal Sergei Akhромiev, chief of the General Staff, grimly admitted the P-3's effectiveness. "I always know where my submarines are. I look at where the P-3s are flying. That's where my submarines are." It was the ultimate admission. The P-3 Orion, America's ugly propeller plane, had rendered the ocean transparent, and the Soviet Union's most expensive, most strategic assets were naked.
The engineering of the P-3 Orion, culminating in the ANU computer, had solved the problem of detection. It had made the opaque ocean transparent. But finding the enemy is only half the battle. The final step in the chain is the kill. For this, the P-3 needed a weapon as smart as its brain, a robotic killer that could finish the hunt. The P-3's ANU system didn't just find the target, it cued the kill. The primary weapon for this was the Mark 46 Mk-46 lightweight torpedo, the Navy's first lightweight homing torpedo designed for air launch. This was the perfect robotic assassin to cap the P-3's data-driven hunt. It was a fire-and-forget weapon, dropped from the P-3's internal bomb bay, often from a low, high-speed pass. Once the torpedo hit the water, its own onboard computer took over. Its specifications made it a submarine's worst nightmare. Guidance. It featured an advanced active or passive acoustic homing system. It could silently listen for the submarine or actively ping for it. Search pattern. If it missed on the first pass, it was engineered to not give up. It would automatically begin a pre-programmed snake or circle search pattern to reacquire the target. Speed and depth. It could travel at over 40 knots, significantly faster than any Soviet submarine could flee, and could dive to depths greater than 1,200 feet, allowing it to chase targets into the deep thermal layers. Warhead. It carried a nearly 100-pound charge of PBXN-103 high explosive, more than lethal enough to rupture a high-strength submarine pressure hull. This was the final link in a chain of apex engineering. The SOSUS network provided the clue. The P-3's ANU computer found the target, and the Mk-46's internal computer finished the job. It was a fully integrated digital kill web that stretched from the seabed of the GIUK Gap to the weapons bay of an aircraft flying 15,000 feet above. The P-3 Orion was the undisputed star of American airborne ASW, but it was not the only player. The U.S. Navy's strategy, honed over decades, was one of defense in depth, creating inner and outer zones of control. The P-3 and its carrier-based counterpart, the S-3 Viking, formed the two key pillars of this airborne defense. The P-3 Orion was the patrolman. It was a land-based aircraft, and its 17-hour endurance gave it the legs to prowl the outer harassing zone, the deep ocean choke points like the GIUK Gap. Its mission was strategic, to find, fix, and track the Soviet fleet, long before it ever got close to an American carrier. The S-3 Viking was the bodyguard. Nicknamed the War Hoover for the distinctive sound of its turbofan engines, the S-3 was a jet built for the carrier deck. It traded the P-3's extreme endurance for the fast response capability needed to launch from a catapult. Its mission was the inner firing zone, providing immediate submarine protection for its parent carrier group. If a Soviet sub leaked through the P-3's patrolman's screen, the S-3 was the shotgun, the carrier's personal guardian. This two-aircraft bridge gave the U.S. Navy a layered, nearly insurmountable defense. The P-3's digital ANU system provided the strategic, wide-area picture, while the S-3's advanced sensors provided the tactical, close-in protection. Together, they dominated both the deep ocean and the immediate tactical battle space.
The P-3 Orion, an aircraft born from the commercial failure of the L-188 Electra, joined an elite, almost sacred handful of military aircraft alongside the B-52 Stratofortress, the KC-135 Stratotanker, and the C-130 Hercules, that the United States military has operated for more than 50 years. The secret to this incredible 60-year service life was its upgradability. The P-3's 1960s technology did not make it a legend. Its airframe did. The spacious and structurally over-engineered Electra body was the perfect truck, with ample room, cooling capacity, and electrical power generation. This made it easy to change out the electronics inside. The P-3's history is a story of continuous digital evolution inside an analog body. The P-3A, 1962. The original model with state-of-the-art analog sensors and a human tacho performing manual calculations with a grease pencil. The P-3C, 1969. The first revolution. The digital ANU computer system was introduced, automating the hunt. The P-3C Update 3, 1984. The second revolution. This baseline configuration added modern technology and improved acoustic sensors, including the powerful IBM Proteus acoustic processor, allowing it to track the new ultra-quiet Soviet submarines. The AIP, 1990s. After the Cold War, the Anti-Surface Warfare Improvement Program gave the P-3 new life. It added imaging radar, electro-optic sensors, and full C4I compatibility to counter new, non-traditional threats. This innate adaptability
meant that when the Soviet submarine threat vanished, the P-3 found new missions. The ultimate subhunter was so versatile that it became a premier overland surveillance plane, used to scout ahead of ground convoys and hunt insurgents in the arid, landlocked country of Afghanistan. It was used by U.S. Customs for counter-narcotics patrols and by NOAA as a hurricane hunter. The airframe was simply too good, too reliable, and too economical to retire. The P-3 Orion was finally retired from frontline U.S. Navy active-duty patrol squadrons in 2019, with the last squadron completing its transition in 2020. Its replacement is the Boeing P-8 Poseidon. The P-8 represents a modern trade-off. It is a jet, giving it faster transit times than the P-3, but at the cost of a bit higher fuel burn on station. But the P-8's very existence is the P-3's final victory. The P-8 Poseidon is a modified civilian airliner, the Boeing 737. It is a big-body airframe stuffed with the most advanced, integrated sensor network on Earth. The fundamental doctrine that the P-3 Orion established in 1962, using a reliable, economical, ugly civilian airliner as a truck for a revolutionary computerized sensor network, was so profoundly successful that the U.S. Navy used the exact same playbook 60 years later. The P-3 Orion did more than just hunt submarines. It defined the very mission, the very engineering philosophy that its 21st century successor now inherits. It was, and remains, the definitive solution to making the ocean transparent.